Today we're talking about a crisis in the American energy system, and we have three people who are directly solving that issue. They're going to be talking about creative solutions to the energy crisis. I'm going to start quickly by introducing them. The first is Paige Crayon. She's the GM of Tapestry, Google's electric grid moonshot. Her team is currently helping Chile, New Zealand, and PJM to model their electric grid. PJM is the largest energy market in the United States, and in many ways it is ground zero for many of the issues that we're seeing in data center power demand. Mitesh Agrawal is the CEO of Positron, a company that is making chips that make AI inference and GPT queries exponentially more efficient. He recently transitioned from his role as the chief operating officer at Lambda, a multi-billion-dollar valued cloud infrastructure company focused on AI and NVIDIA GPU-powered services. And finally, Nelson Abramson. Nelson is the CEO of Veris, a company that is working to modernize data centers by making them flexible for the first time. Nelson was Twitter's head of infrastructure and Google's director of engineering. He spun Veris out of Google's Sidewalk Infrastructure Partners and has brought together an all-star team to solve this problem, including the former head of energy at Meta, a VP at EdgeConneX, Google, Verne Global, etc. A great team. All right, so let's start by setting the scene. We're seeing a huge surge in data center power demand. Big tech is spending hundreds of billions of dollars building data centers, and their main limiting factor is access to power. They're collectively betting they can scale their compute and win the AI arms race. And the projections for where energy will go is uncertain. So my first question to you, Paige, how much of this data center energy demand is real? We see headlines every day, but we don't know where it's going. What do you think?
Thank you for the softball. And thanks for having us. It's great to be here. I've been thinking about energy and the electric grid and growth in energy since before November of 2022, when ChatGPT was launched. And for those of you who have been following this story, if you were looking at the annual International Energy Agency report in 2023, they would have been raising their hands. This is, again, just a few months after sort of the big boom in AI, and saying, we don't have enough energy. In that report in 2023, they said, so the electric grid is humankind's largest machine. It's 80 million kilometers of physical infrastructure all around the world. It took us 130 years to build it. The International Energy Report in 2023 said we need 80 million more kilometers of grid by 2040 to meet our electricity needs globally. So that is before we even added energy. So when I talk about demand, I think there's going to be robust debate on, is it over-projected, is it under-projected, how fast will the chips and the optimizations come aboard, how helpful will it be, and I hope you have a wonderful, robust discussion on these topics. What I know for sure is humanity needs more electricity. Period, full stop. We're going to do a lot of things with it, and we're going to do a lot of things that are going to help our communities in many different ways, and it's an all hands on deck. And to me, I say whether it's 5x or 2x or 3x, that doesn't change what we do today. We need to do a lot of things very differently, and no matter what, we're going to at least be doubling the electricity that we need around the world.
Doubling in what time frame, you think?
I am bullish that 2040, so IEA is well researched, and unfortunately everyone who has opined on this topic has underbet. We have exceeded our needs over and over and over again. So if we say we need to double it by 2040, we probably need to double it by 10 years sooner than that.
Which is crazy, because you're talking 80,000 kilometers in the United States and the biggest infrastructure in the world, and you need to basically double that infrastructure in a time where we can't build large infrastructure.
Infrastructure, or use what you have more intelligently, which is my leading nugget for the rest of the conversation.
That. Good nugget. All right, what are the solutions, you think? Knowing that we can't expand the infrastructure as quickly as we need to. We got chips, maybe. We have flexible data centers. Mitesh, maybe let's start with you and think through your vision of how we could potentially solve this.
Yeah. I think one thing I'll say to kind of corroborate with Paige is it doesn't matter whether we need 2x, 3x, 4x. We just have to build as much as we can. And whether that becomes a 5x, that's good for us from that perspective. Also, that 2x projection, it's very interesting to hear Paige, because she's saying 2x of all power. So power is not just consumed in data centers or by companies' energies today. It's like every consumer, everything, right? So doubling of that for that, it's a huge, huge number. In terms of as you said, there's many ways to really make efficiency of power better. So for every watt that we are consuming, it's important that not only we increase the number of watts we produce by any means necessary. I am really a huge on that side of like by any means necessary we should increase the energy production, but we also should make sure that what we are getting from that energy is also multiplied multiple x, because we will need the combination of two to really support all of humanity's growth. So obviously I'll speak about the thing that I am focused in and kind of really spend a lot of my time, which is the chip side of it. I think everyone from NVIDIA to Google to AMD to a lot of silicon startups like my own company Positron, we're all focused on how can we get more intelligence out of every watt. We actually measure this very, it's one of the driving KPIs for the company, performance per watt. We really, really focus on it. In fact, in every kind of pitch deck and everything that we present to the world, we want to make sure that we are producing 2x, 4x, 5x more performance per watt compared to what is the current leading edge solution. And you want to continue on that. You can't just do it once and say you've done it, because every single year it's moving forward. So that's my way of contributing effectively more energy to the world, there.
Nice. More powerful chips is one direction, but I think another, we design our electric grid for peak demand. That's the only way we design our grid, but we don't use peak demand most of the time. And so, Nelson, I think your solution is one of the most impactful and short-term solutions that we need to think of redesigning our grid, and we'd love to hear about it.
Oh, thank you. And two thoughts on the underlying demand first. I think the first is that the demand for data centers and compute and chips overall, it's easy to look at it as a recent problem, but it's an exponential curve. And so I wish I could say it was with intention when I got into the industry 25 years ago, but of course it's understood backward, live forward. But data center demand, overall compute demand has been 25 to 35% compound annual growth for the last 40 years. It's just that, like, the metaphor of looking at a pond with an exponential growth of lily pads, you don't notice it on like the third day, the day 2 or 3 before it completely covers the pond was exponential, but it really started 30 days ago. So you have that same underlying thing, and the other piece being the reason we've been able to afford data centers and this growth of compute from an energy perspective for the last 40 years is efficiency and deindustrialization. And so, like, LED light bulbs, very underappreciated driver of underlying efficiency of energy, but like that bought us 20 years. It's crazy if you look at the energy consumption graph. But what we see, even all that in context, and then you watch the demand growth, the grid itself, when we talk about the grid being full or out of energy, we're really talking about a very small fraction of the year, right? So if an 87-60 distribution, you think about, okay, when is the grid full? Well, it's full at 4 p.m., the end of August, when everybody goes home and cranks their air conditioner because it's hot, and the sun's not shining because it's cloudy, and it also happens to be calm from a wind perspective that day. And so you have both a demand side crisis and a supply side crisis, and that lasts like 4 hours, maybe 8. And when that happens, when you can project that happening, because it really does happen, and for that, you're like, the grid's full. But that's not every day, right? So you have that happen like hundreds of hours a year, and then the whole rest of the year, you're in this very sharply downsloping part of the distribution, where the grid is 50% full. And so the question is, how can you combine this reality, which is we don't use the same amount of energy at midnight as we do at 9 a.m. or at 4 p.m., with the concept that, like, if you're trying to run a data center, if you're trying to train a large language model or run your product or whatever it is, you don't, if you're running a consumer-facing product, you can't just say, hey, we're not going to answer queries at 4 p.m., right? It doesn't work that way. So the question is, how do you combine the idea that the energy consumption, the grid needs to be managed differently at different times of the day, different parts of the year, with the fact that the customers need to run the same things all year round. And you also don't want to train your engineers like, oh, hey, the software engineering side should be managing this. That's not the right part of it. And so we take all of these pieces together, and the kinds of data centers that we build form that impedance match between what the grid needs and what the compute users need.
And I think it can't be underestimated how hard a problem that is to solve, because data centers, you've been in the industry 25 years, there's a very traditional structured way of thinking where you have to have a reliability rate where you're down for a minute at a time over the entire year. And suddenly you're saying, hey, you need to shift this to have hours of change in your compute. How do you deal with shifting a massive infrastructure group and a entrenched mindset to say, how do we creatively solve this problem we're all facing?
Oh yeah, no, I mean, and to be fair, it's both actually a hard problem technically and operationally, and it's legit. Like, so when you think about chip fabs, which is like maybe the closest analog, if you're running a chip fab, you measure downtime in terms of minutes. Because they're like, you got to do a software maintenance and take equipment offline at the chip fab. You're like, okay, you have one Sunday at 1 a.m. and you get 15 minutes of downtime because it's so expensive. That's how you have to think about it. And you have the same kind of problem, right? Where if you want to take a data center offline, the data center itself costs something, but really your problem is the servers that are inside of it. There are only so many chips, and the customers that you're not interacting with or interacting worse with, and therefore getting lower conversion rates or whatever. And so building a system requires both like the hardware engineering layer, so you have the electrical mechanical systems, which of course generally not designed to turn off and on, right? Like these systems like to run at the same thing, the same load all the time, as well as the software operations layer, where you need a software system, a control system that can understand that and manage these systems correctly, and then run it in a way aware of how the grid operates, aware of how the compute system operates, and cross all of these technical and organizational boundaries across the customer world as well as inside of our own world, and operate it successfully, right? And form that impedance match, get everybody comfortable. It's juggling a lot of pieces.
Paige, I'm wondering, you've seen a lot of international approaches to how grids, how people design grids, how they operate them, how they are thinking about building them. We're competing with China in a lot of ways for this AI race, but other countries as well are facing electrification challenges. And I'm curious, what can we learn from the international community of grid operators that they should bring home to the US and we should adapt here?
Well, I think in good news, this is a challenge everywhere in the world. So we're sort of all in it together. And, Italy doesn't compete with Chile, and how you produce power doesn't compete with. So we grid operators actually get on the phone and tell each other, hey, I tried this, it worked. And so there's a good exchange and transferability of lessons. But as you pointed out, when Tapestry started, we sort of looked at places in the world where we could learn as quickly as possible about this problem, because as I say to my team, the physics are the physics. So what we learn in Chile about what happens when wind farms are full on and we have a large load can be transferred any place that has that same profile. And so one of the first places that we started working at a national level on this issue of how do you build out transmission is the country of Chile. One, because it's an incredibly challenging physics problem. It's a long, narrow grid with, if you're a power systems engineer, which you might not confess to in this room, some of my favorite engineers are, it's like incredibly challenging to manage a grid that is not radial, right? You can't cheat, you need a lot of inertia, right? So if we could figure out how to do that in a long, narrow grid, we could transfer that elsewhere around the world. Number two, they have a lot of variable and power system driven connections to the grid because they have a lot of solar in the desert and they have a lot of wind, et cetera. Also incredibly challenging to model. But finally, the thing that really made us sort of start in Chile was they have publicly available data about their grid. So for those of us who want to, Tapestry actually applies AI to help figure out how to run the grid to be able to build more energy for more AI. And so we knew that we were going to, be able to run models tomorrow as opposed to spending a year kind of collecting data, cleaning data. The reality of the power grid is we just, for decades, we haven't really instrumented our systems the way that deeply digitized networks are run. And so going to a grid operator and saying, I need, millisecond information about every node on your network for the last 10 years, are like, we don't have that. Not because they're not good at their job, but because it wasn't necessary. And so one of the things that was really interesting about Chile is their information is, you can go on the web and download it. I'm not advocating for or against it, but that's the policy they have. Their KML file, and it allowed us to get started really quickly. Now we can look at simulations and we transfer that same information if we see a profile that's similar to the US or in New Zealand where we work. And so again, for me, the optimism is that not every country has to learn these insights on its own. We can really share these insights once you instrument and run these algorithms. So to me, that offers a lot of optimism in what we can do, globally.
It's interesting. So you're saying we should open source our data potentially, which I agree with, by the way. But
I'm saying we should carefully be thoughtful about, but one of the challenges to drive more innovation is access to highly credible information from which all of these wonderful entrepreneurs can do their magic.
Yeah, I used to work at ARPA, the Department of Energy's Advanced Research Project Agency, on data center algorithms and stuff, and that was the biggest problem we had, is we couldn't get access to data, and the grid operators wouldn't trust us because we didn't have their data, and they wouldn't give it to us. So it's an interesting issue, and I think that's part of where Mitesh and Nelson, you face these kind of multiple systems. You're dealing with utilities, and you're also dealing with data centers, and you're dealing with the local people who don't necessarily want these data centers in their backyard at the same time, and you have to convince them all. Mitesh, I'm curious, what do you think about when you're trying to bring a new chip to the system? You know, everyone's saying we only do NVIDIA chips, maybe AMD. How do you think about how you win people over to say, hey, we can be more efficient, our system might be smarter, you need to trust us?
Yeah, I mean, I'll give you a real answer. We are already working on this very much with the government, within the government ecosystem too, right? So first and foremost, just a general answer to that is I think NVIDIA GPUs, AMD GPUs, Google TPUs, they're brilliant pieces of silicon. They work very well for different types of applications, right? And I think just like in most aspects of life, we have really determined most efficient use cases for each type of technology. I think in the silicon system, you will see that. You know, video generation will have amazing silicon dedicated for it, you know, because of some feature of the chip itself. Same thing with training models, and same thing with other use cases of inference, right? So I think for people that believe that it's like a one chip that will work across all, it will work, but it won't be the most efficient. So automatically, market forces will drive efficiency. So that's a general answer. But to your case, in the you know, at Lambda, I used to run our entire data center setup and deployment, and then one of the big things was even if you could convince the grid to give you the power, then you have to convince the municipality to agree to it, then the local people, and things like those, right? And I think part of it is we see now efforts, especially like state of Georgia, where actually at Lambda we had trouble getting power, and then now we are seeing and now we understand why, because we're seeing an initiative from them where they're like, okay, well, for this given amount of power, what's the output that you're getting? And this is where like Positron goes in and says that, hey, for this current state of those art models, we can drive this much more kind of utilization or use cases from it, right? And then you get almost integrated into part of their kind of whole infrastructure planning. So, hey, if they're going to allow a data center to be built near Atlanta, then part of that needs to go for Positron chips. Part of that needs to go to NVIDIA. Part of that needs to go to something else. And that's a big way, you know, I'm literally sharing commercially how, you know, company like an upstart like Positron can get into it, and then similarly how big companies can also continue to drive that type of feature. So it's actually a working together kind of setup with the municipalities, with the grid providers, with the government, because they need to understand for every watt of energy that they're providing, kind of what's the output, what is needed for, and then second, what are we doing to continuously improve it? So that's a real world example that we're seeing.
Nice. You're basically making the business case in a time where margins can be tight in this industry,
Yeah.
increasingly with competition. So an area that I want to understand is how does this affect American citizens? We're seeing energy rates go up, you know, 10, 15%. Some people are saying it's hyperinflation in our electric bill costs. And there could be a opportunity for data centers to provide a lot of revenue to utilities so that customers don't have to pay as much for the infrastructure. The data center is paying for it. But we're not necessarily designing the system that way. Nelson, I think the way you're thinking about the system, using the assets we have to be more efficient, could potentially be a solution to that. Go through the question of how this affects the average American citizen and where it could go if we designed it right.
Yeah, one of the things that we're able to do by bringing flexibility and grid interactivity along with our data center is the ability to drive up utilization for the utility itself across the whole rest of the year where it's not constrained. And if you think about it just very simply, the way utility is structured, they take all their costs to build, run, operate the grid, and that's a combination of very high fixed costs, right? The CapEx to build the wires and the substations and the power plants, and then the OpEx, so fuel costs, maintenance, these kinds of things. And they divide it by the number of kilowatt hours they sold, and that's simplistically your dollar per kilowatt hour that you pay, well, plus a guaranteed profit margin. That's roughly the way that it works. And so if you take the same underlying grid and you drive average utilization from, call it 40 or 50% to 60%, which would not be a particularly unimaginable change, now you are taking the same underlying fixed cost. Obviously, you have some marginal increase of cost because now you're paying fuel costs for whatever is not renewable in addition, but most of it is driven by underlying fixed costs. And you can now take that same pool of fixed costs and divide it across 20% more. Now, you know, that is very easy to see as opposed to a world where you take the same underlying utilization, where it's average of 50, And you now start adding lots and lots of peaking capacity, which is what you have to do when you add a traditional set of loads that do not have flexibility.
So just to translate a bit of that, the peaking capacity, like there are ways that you can make energy cheaper or more expensive. If there's suddenly a demand of a very large peak of energy, you'll use a gas power plant that costs a lot more to power than solar or wind might in that time period. And if you can basically allow us to not have to build that peaking capacity, you can lower the cost of generation a lot. And if you can use the same resources, the same assets over a larger amount of demand, then you drop costs. And so that's where someone like Jigar Shah, who used to run the loan program office at DOE, is saying we could drop our electricity costs. They don't have to go up inevitably if we can design the system right. And I think that's really the dream of what, designing the grid better, using more flexible data centers, having more efficient chips, having these data centers soak up power but also pay for it. We could drop our electricity bills. They don't have to go up.
Yeah, absolutely. And I think there's a lot of elements working in the utility space now. I think they're all getting kind of munched together, but I think if you just sort of step back and look at it at the 10,000-foot view, you're like, what you want is the most efficiently packed, highly utilized grid possible on the lowest underlying fuel cost, highest underlying renewable energy fraction that's possible. Right? That's sort of the outcome that you want. And so you think about, how do we make that true? Well, it's the same if you're talking about VMs as if you're talking about manufacturing, as if you're talking about utility grids, which is, well, you want to have as most flexibility as possible in your underlying on the demand side and on the supply side, and you match them, and you either do time division multiplexing or whatever the underlying system supports, and you pack it in as much as you can, and then your unit cost is as low as possible.
Nice. I want to leave space for a question or two if anyone wants to throw one in. You, sir.
How much of their energy is going to inference and how much is going to training? Because obviously, inference, you do need to keep running for the customers. Training, you can pause during a grid peak.
So nowadays, the underlying demand is dominated by training. That's because we're in a world of everybody trying to figure out what's the right set of models, what is the right customization of those models to then turn it into product. And so as a result, training dominates. I think everybody expects that to flip, which is like, you don't make money on training. Well, I mean, maybe something like Lambda does. But outside of infrastructure, the platform, infrastructure as a service companies, the end customer-facing products are not about training, they're about inference, and so it all has to flip to inference. But I would expect it to go sort of back and forth, square wave style or sine wave style more realistically, which is the way that it's worked across all the software technologies that I've seen over a year, which is like you go back and forth.
But specifically, you said the problem is people don't want to shut down at the peak, but training is fine to shut down at that short peak.
I mean, we don't have enough time to go into it. It is harder to describe. It's at one level, yes, training is easier to shut down than inference because you're not dealing with live customers. But if you think about the large-scale systems, why don't chip fabs shut down? Like, they're not direct. It's not like they're customers at the end of the facility waiting for the chip to fall out. The reason is, like, it costs so much to build, operate, and run this thing, and the efficiency of utilization of that factory dominates the profitability of the company. Right? So like it's not simple. So we build a system that allows the customers to not have to experience the interruption and still deliver the flexibility.
All right. Thank you all for being here, and thanks for the time.